Hello everyone. In the previous section, section 3.2, we solved linear systems belonging to each of the three cases: one solution, no solution, and infinitely many solutions using Gaussian elimination. We will now examine the augmented matrices in REF we obtained when solving these systems. For each of the three cases, we will answer the following questions. What does an augmented matrix in REF look like? And what is the rank of the augmented matrix? And what does it tell us about the number of solutions? That's what we're interested in this section, the number of solutions of a linear system. In the following examples, AUG will denote an augmented matrix, while A will denote the corresponding coefficient matrix. Let's look at case 1, linear systems with a unique solution. We're going to look at example 3.2.7 and example 3.2.8 again. We had these examples in section 3.2. When we were solving the corresponding linear equations, we reduced an augmented matrix and obtained this one in row echelon form. We also found the solution xyz equals 8, 3, minus 2. Now, what is the rank of the augmented matrix? Well, the rank is the number of leading entries, which is 3. The rank of the coefficient matrix is also 3. Remember that the coefficient matrix is the smaller matrix, the matrix that does not contain the column of constants. And so the rank of this coefficient matrix is also 3. The number of variables of the linear system is 3, and there are no free variables. Every variable is a leading variable. In example 3.2.8, we also found an augmented matrix in row echelon form, and we found the solution to be xyz equals 6, minus 5, minus 3. The rank of the augmented matrix in this case is again the number of leading entries, 1, 2, 3, which is 3. And the rank of the coefficient matrix is the number of leading entries in that coefficient matrix, which is also 3. And the number of variables is again 3, and the number of free variables is 0. All of the variables are leading variables in this case. Now, in general, what does an augmented matrix in REF that corresponds to a linear system with a unique solution look like? Well, let's look at this takeaway. In general, an augmented matrix in REF that corresponds to a linear system with a unique solution looks like, and here we're given two examples. Each star is a non-zero real number, and each square is any real number. What these augmented matrices have in common is that every single column corresponding to a variable, x, y, z in the first case and x, y in the second case, contains a leading entry. Now let's compare the rank of the augmented matrix and the rank of the coefficient matrix. The rank of the augmented matrix and the rank of the coefficient matrix in the case where the linear system has a unique solution are equal. We saw that in these two previous examples. The rank of the augmented matrix and the rank of the coefficient matrix were both 3 in both examples. And what if we compare the rank of the augmented matrix with the number of variables? Well, in this case also, we get that the rank of the augmented matrix is equal to the number of variables. And we also have that the number of free variables is equal to 0. All variables are leading variables. Now, what about the case when we have no solution? Let's look at case 2, linear systems with no solution. In example 3.2.9, we found this augmented matrix in row echelon form, and we did not find a solution. This is an inconsistent system. What is the rank of the augmented matrix in this case? Well, how many leading entries do we have? 1, 2, 3. 3 leading entries. What is the rank of the coefficient matrix? That's the smaller matrix that doesn't contain the column of constants. The rank of that matrix is actually 2 in this case. So we see that the rank of the coefficient matrix is not equal to the rank of the augmented matrix. Now remember that we were able to conclude that the corresponding linear system was inconsistent because this third row in the augmented matrix gives us the equation 0x plus 0y plus 0z equals 4, which is inconsistent. 0 is not equal to 4. So let's look at the takeaway. An augmented matrix in REF that corresponds to a linear system with no solution looks like, and again here we're given 2 examples, and again each star is a non-zero real number, and each square is any real number. What do these augmented matrices have in common? Well, each of them have a leading entry in the column of constants. And because they have a leading entry in the column of constants, in each of these cases we'll get an equation of the type 0x1 plus 0x2 plus 0x3 equals a non-zero number. Or in the second case, 0x1 plus 0x2 plus 0x3 plus 0x4 equals again a non-zero number. Now let's compare the rank of the augmented matrix and the rank of the coefficient matrix. When there is a leading entry in the column of constants, we have that the rank of the augmented matrix is greater than the rank of the coefficient matrix. Now what happens in case 3? So case 3 is the case when linear systems have infinitely many solutions. And we're going to look at examples 3.2.11 and 3.2.12. In example 3.2.11, we ended up with this augmented matrix in row echelon form, and we ended up with this solution with 2 parameters. What is the rank of this augmented matrix? Well, let's look at the number of leading entries. 1, 2. We have 2 leading entries, and so the rank of the augmented matrix is 2. The rank of the coefficient matrix is also 2. The number of variables in this case is 4, and the number of free variables is 2. x3 and x4 were free variables that we assigned parameters to. In example 3.2.12, we got this augmented matrix in row echelon form, and we got this solution with 1 parameter. The rank of the augmented matrix here is 1, 2, 3, and the rank of the coefficient matrix is also 3. The number of variables was 4, and the number of free variables is 1. Now in general, let's look at this takeaway. An augmented matrix in row echelon form that corresponds to a linear system with infinitely many solutions looks like, here we have 2 examples. And again, each star is a non-zero real number, and each square is any real number. Now, what do these augmented matrices have in common? What they have in common is that at least one of the columns to the left of the column of constant terms does not have a leading entry. And we saw that in the 2 previous examples. In example 3.2.1, 2 columns do not have a leading entry. And in example 3.2.12, 1 column does not have a leading entry. Now what can we say about the rank of the augmented matrix and how it compares to the rank of the coefficient matrix? They're equal. For a linear system with infinitely many solutions, they're equal. We saw that in the last 2 examples. The rank of the augmented matrix and the rank of the coefficient matrix was 2 in the first example and 3 in the second example. Now if we compare the rank of the augmented matrices with the number of variables, we see that they're not equal. we always have that the rank of the augmented matrix is less than the number of variables. And also, linear systems with infinitely many solutions have free variables. The number of free variables is greater than 0. In the next video, we'll summarize some of what we found in these takeaways in a decision tree, and then we'll be able to determine the number of solutions that a linear system has by examining the corresponding augmented matrix in row echelon form.